I've been working on this particular type of problem for quite a while, and I have collaborators. In fact, I started working on this, in the 80s with Lewis, who published one paper, and then, other co-workers are Christopher Doble and Jean-Paul Doignon. I start with the idea that when we deal with geometric laws or scientific laws, we practically never mention the units. This is a bunch of things to give you the idea. And everybody is comfortable with that. We don't need to mention the unit because the form of the law is invariant. When you change the unit, nothing changes in the equation. In fact, any mathematical model whose form would be affected by change of unit would be a very poor representation of the world, simply because the units are not part of the world. But this is an invariance property. And when we formalize that invariance property in the right way, we end up with a very powerful axiom. And when we combine this axiom, this abstract axiom, which I will give you in a moment, with abstract properties, abstract but intuitive, we combine the two, and we can derive from that the exact form of the law, possibly up to the values of some parameters. And I will give you a number of examples of that. One example of this talk, which I will deal with at the end of the talk, is the Doppler effect, the relativistic Doppler effect. And it's the change of the frequency of the wavelength of a wave or other periodic event from an observer moving relative to that sort. And an example of the Doppler shift is when you drive your car, and there is a police car that comes next to you. The sound is going to be affected depending on the speed of your car and the speed of the other car producing the sound. This is a picture illustrating the Doppler effect. You have the star in the middle is the origin of the wave, and then you have an observer, which can be in a spaceship, moving very fast. And so you see that if you move, in the wave, the frequency of the wave is going to be altered by the speed of your movement. And the equation describing that is which I call dE, and it's the equation which is put there. L of lambda v is equal to the product of lambda by the square root of that ratio that you see. C is the speed of light, lambda is the wavelength, and L of lambda v is the wavelength of that light measured by the observer. Note that when v equals 0, that means you don't move, there is no effect. The square root is equal to 1, and lambda is unaltered. On the other hand, when v tends to the speed of light, the value of the ratio ends up being 0. You don't see anything. In the last part of this talk, I will show how the abstract axiom that you see, which I call R, combined with the meaningfulness axiom, might lead, under some general condition, to the function which is, the last equation in the page, which is lambda multiplied by something in parentheses. In other words, it's almost equal to the Doppler effect, except that instead of the square root, you have a power psi. And the equation R is an axiom formalizing an abstract representation of the mechanism inducing the Doppler effect in special relativity. So the operation O plus represents the relativistic addition of velocities. So the left side of the equation is an iteration of the function L, and the right side is adding a speed W to the speed V. And what the equation is saying is that the iteration has the same effect of adding a speed. Now, you might object to this equation R because it's not terribly intuitive. What's the evidence that this iteration is going to have the same effect as adding a speed? However, you can show that the equation R is equivalent to the equation M, which is much more intuitive. And this equation M is saying that if you have an order L lambda V small or equal to L lambda V prime, and you add the same speed V on both sides, the order is going to remain the same. And that is very intuitive. That you're ready to accept that. So the idea is that either of these two axioms combined with meaningfulness is going to push you in the direction of getting the exact equation for the Doppler effect. And not only the Doppler effect, also the Lorentz-Fitzgerald equation. So this talk has 4 parts. I will motivate the meaningfulness axiom. I will define it for a function of 2 ratio scale variables. And then I will give you one in details, an introductory example of a meaningful derivation, which is Beer's law. And then after that, I will give you a tentative derivation of the relativistic Doppler effect. Now, the trouble with an equation such as dE is that it's ambiguous in the sense that the units are not specified, so I don't exactly know which physical situation I'm referring to. For example, writing L73 has no empirical meaning if I don't specify, for example, that the pair 73 refers to 70 meters and 3 kilometers per second, respectively. Now, such a parenthetical reference is standard in science, but it's not useful for our purpose because we want to define an invariance with respect to the unit. And to rectify the ambiguity, I propose to interpret L of lambda V as a shorthand notation for L11 LV, in which L11, the 11, the subscript 11 represents the initial or anchor unit. If I describe the phenomena in terms of other unit, that means that I have to multiply lambda and V by some constant, which are, alpha and beta. So that, and L, so if lambda is multiplied by alpha, L has to be also multiplied by alpha and the speed of light by beta. And so that defines another function, L alpha beta, which is different from L11, but from an empirical standpoint, it carries exactly the same information. For example, if the new units are kilometers and meter per second, then the two expressions, L subscript 10 to the minus 3, 10 to the 3, 0.07, 3000, and L73 equal L11, 73, while numerically not equal, describe the same empirical situation. This points to an appropriate definition of L alpha beta in the case of the Doppler equation. It turns out that when we get the right definition, that what we have to write is L alpha beta lambda V is equal to lambda multiplied by the square root of 1 minus v divided by beta c and 1 plus v divided by beta c. This is the equation that will result from a suitable definition of the invariance axiom that I'm looking for, the meaningfulness axiom. It's not a definition, I'm just announcing that it's coming. And the connection between L and L alpha beta is actually the equation that you see there, 1 over alpha, L of alpha beta, alpha lambda beta v is equal to L lambda v.
On the previous slide, there appears to be alpha, a factor of alpha missing, and
Possibly.
in that equation.
Why?
Because lambda is being scaled by in the alpha unit.
Yeah, it goes away.
Okay. So it goes away on both sides.
It will be eliminated by the definition of meaningfulness. Don't hesitate to interrupt. Now, in the framework of the meaningfulness axiom, it will turn out that the relation L of alpha beta squiggle L mu v is an equivalence relation, because it will be true if and only if you have the equation which is on the the last equation on the screen. And this equation is actually what will become the meaningfulness equation in this particular case. And what that means, of course, is that the squiggle relation is an equivalence relation, is reflexive, symmetric, and transitive by definition. Now, you may complain about that, my notation, because if we start writing the equation of physics or geometry that way, life would become very hard. But this is only temporary. When you have used meaningfulness to derive the theorem that you want, you can get rid of this notation and go back to the original notation. In fact, the last equation on the board tell you exactly how to do that. 1 over alpha L of alpha beta lambda alpha lambda beta v is equal to L of lambda v. So this example makes clear that if we want to define meaningfulness, the definition has to apply not to one function, but to a collection of functions. And I will call each of these functions a code. So let's start with the definition. So let's J1, J2, and J3 be 3 non-negative real intervals. And suppose that script f is a collection of f alpha beta of function, with alpha beta being positive reals. And that's a collection of code, and the initial code is f equal f11, and that one maps J1 cross J2 onto J3. In other words, the J1 and J2, J3 apply only to the initial code, not to the other one. Why? Because if you change the unit, this interval may automatically be changed. And here is the definition of meaningfulness. Let delta 1 and delta 2 be two rational numbers. The collection of code, script f, is delta 1, delta 2 meaningful if for any x1, x2 in J1, J2, and alpha, beta, mu, nu in the product of the positive real by itself. We have the equation which is written on the board. I won't read it, you can read it. Now, we have two new invaders here, which are the delta 1 and delta 2. The point of delta 1 and delta 2 is this is a very general definition, right? The point of delta 1 and delta 2 is to specify the unit of the function with respect to the unit of the variables. And I will illustrate in a second how that works. Now, I will especially deal with a special case of that definition, which is one in which the unit of the function is the same as the unit of the first variable. And that's where the delta 1 and delta 2 will play a role. I put delta 1 equal 1 and delta 2 equals 0, and then your meaningfulness equation become the one that you see in the just after the equivalence. Okay, 1 over alpha, f alpha beta, alpha x1 beta x2 is equal to 1 over mu, f mu nu, mu x1, mu x2. So that's your basic general meaningfulness equation. So let me give you an example. I told you before that what was nice about the meaningfulness axiom is that in the framework of meaningfulness, intuitive properties, formal but intuitive, might lead you to the exact equation that you're looking for. And Beer's law is a very good example of that. So one example of this abstract intuitive equation is the one which is written in the middle there. F of f x y z is equal to f of x comma y plus z. And you will see that in the framework of meaningfulness, this would imply Beer's law. But I first have to show that, or we need that. Okay, so I told you, you have this abstract intuitive equation. Then the next step is to transform this meaningfulness equation into an abstract representation. And you do that by using functional equation. In other words, if I go to that equation here, and I go into for example, Janos Axel function equation book, I go to the right page, and I discover this lemma. So if you have a function which is defined on the, cross product of two intervals, the code is translatable in the sense that the equation that you just saw, if and only if there exists a function f satisfying the equation f of xy is equal to f of f minus 1 plus of x plus y. So that's step one. We haven't used meaningfulness yet, but we use an abstract axiom, and then we use functional equation to derive an abstract representation. After that, we introduce meaningfulness. Okay, Beer's law. Now, what is Beer's law? Beer's law is what is happening when you have an incoming light which is going through an absorbing medium, and then the light that comes out may be weaker. And the equation is called, Beer-Lambert law, Lambert-Beer law, Beer-Lambert-Bouguer law, etc., etc. And this equation describes the attenuation of light due to an absorbing medium. Now, I have to connect this situation with the translation equation. So let's do that. So the incoming light is x. The power of the absorbing medium is y. So what comes out of that, the green medium is f of x comma y. Then suppose that light coming out is getting to another medium, which has absorbing power z. So what's coming out is the left of the top equation there, f of xy comma z, right? Now, if you assume that the two absorbing power are additive, you get the equation which is your translator equation, okay? And that seemed to be fairly intuitive, right? Now, I need another function, I need another hypothesis, which is number 2 down there. Suppose that the incoming light, for some reason, is either, its power is increased or decreased. For example, instead of x, I have ax, like here. Here, the picture is, imagine that that you have a number of rays getting in, and the black rays are rays which are eliminated. So here, half of the rays are gone, and what I'm assuming that if half of the rays, incoming rays are gone, then half of the outgoing rays should also be gone. Okay, that's the assumption, right? And that leads to the equation which is at the bottom here. A of fxy is equal f of ax comma y. And I call that homogeneous of degree, left homogeneous of degree 1. And here is the theorem. So you have self-transforming. Self-transforming, remember, that means that the unit of the function is the same as the unit of the first variable, okay? So suppose that you have scriptf, a collection of codes which are self-transforming, and suppose that one of these codes, just one, is strictly increasing in the second variable, translatable, and left homogeneous of degree 1. Translatable. Then there is a constant c, such that you have the equation there. F of xy is equal to x multiplied by e to the power minus y divided by c. So that's it. You get Beer's law, all of these intuitive assumptions, and meaningfulness. And the proof is in the paper that I published in 2015 in Equationes Mathematicae, which is a functional equation journal. So this is a good example because the assumptions are very intuitive and the result is very powerful. So the type of proof that you use in that kind of business, there is a schema. And the schema is you start with an abstract axiom, such as translatability. Then you derive using function equation, you derive an abstract representation. You inject meaningfulness, and you derive your power, which is not always as nice as this. Sometimes you have parameters which are not specified. So now, in the book that I published with Chris Doble, we have quite a number of examples of that. And one example is the Pythagorean theorem, which is the first one, the first line. It's easy to prove geometrically that the hypotenuse of a right triangle is an associative function of the length of the two sides. And you go to Janos Axel's book, and then you derive that if the function is associative, then it has to have the form which is in the second column. And then using meaningfulness, you can derive that you have something which is very close to the Pythagorean theorem, except that there is a parameter theta. And using geometrical axiom, it's easy to show that theta has to be equal to 2. Then transitability, we discussed that. Quasi-permittability, that's the third example. So you have f of g, x, y, comma, z, and then the y and the z permute. And the abstract representation is f of x, y is equal to function m of f of x plus g or y. Meaningfulness gives you three possibilities. And then there is one more example. Now, this is only a few examples. And the last slide of my talk will be saying that this is opening the possibility of working, with many people collaborating and constructing a catalog of possible laws that scientists could, look into when they have dealing with a new phenomena. So let's deal with the relativistic Doppler effect. In the case of the Doppler effect, in the example that I just gave you, we could go to functional equation books and look for, nice constraint and nice theorem. But in the case of the Doppler effect, it didn't look like we could do that. So we had to invent, abstract axiom, and that's what we did. We came back with these two axioms R and M. And moreover, we didn't have the abstract representation. We had to figure out the abstract representation. So what, using the proof schema, we have the abstract axiom, we have to derive the abstract representation and try to see whether meaningfulness gives you the equation that you want to get. So the first task is to derive the abstract representation. Well, we did that. But we need to add some other assumption. And so there are 5 conditions that I'm going to give you. And what's remarkable is that all 5 conditions are very plausible. The first one is, a code L is a LFD function, LFD for Lorentz Fitzgerald Doppler. If there is a binary operator, which is mapping the interval 0C cross 0C into 0C, such that the pair L O plus satisfy 5 conditions. First condition, L is strictly increasing in the first variable, strictly decreasing in the second variable, continuous in both, and we have the equation which is at the bottom. If you have an order between, L lambda V, L of lambda prime V prime, and you multiply by a positive constant, then the order remains the same. That's condition 1. Condition 2, L of lambda 0 equal lambda. In other words, if you don't move, no effect. Condition 3, if V tends to C, then L of lambda V is equal to 0. At the speed of light, there is no effect. The operation O plus is continuous, commutative, strictly increasing in both variables, and has 0 as an identity around. Infinitely plausible. And finally, condition 5, either axiom R is satisfied or axiom M is satisfied. When these 5 conditions are satisfied, the pair L O plus is called an abstract LFD pair. And then we have this theorem. Suppose that L O plus is an abstract FLP pair. In other words, satisfy all 5 conditions. Then the following equivalence hold. R is equivalent to D dagger and AV dagger, which the equation is given below, and is equivalent to M. So R and M are the 2 conditions that you have seen. And then you have new equations. So D E dagger is something which is close to Doppler effect, except that you have an unknown function u and an exponent psi. And AV dagger is close to the standard expression for the addition of velocities, except that you have an unknown function u. So the idea is now to inject meaningfulness and to try to derive the Doppler function and the Lorentz-Fitzgerald equation. And it turns out that the Doppler effect is obvious in the sense that if u is the identity function, that's it. You have the Doppler effect, and you have the standard expression for the addition of velocities. But strangely, bizarrely, the Lorentz-Fitzgerald condition is also a special case. So here is a little picture to illustrate the Doppler effect. You have a fast-moving observer, and this observer is looking and measuring a stable rod, and the stable rod is on a line parallel to the line of movement of the fast-moving observer. And this is one of the illustrations of the Lorentz-Fitzgerald equation. And it's possible that the path in which the observer is moving is itself moving, and that gives you the addition of velocities. And so if you examine that situation, all 5 conditions are also reasonable. But remarkably, there is a difference between the 2 viewing situations, right? In the case of the Doppler effect, you're moving in the wave and looking at the wave. Here, you're measuring a rod, which is on a vertical with respect to the movement. Now, if you define u is equal to what you see there, the ratio of v divided by c to the power psi divided by 1 minus the same thing, you derive the equation which is at the bottom, namely L of lambda v is equal to lambda multiplied by 1 minus vc psi, and the whole thing to the power psi. And if psi is equal to 2 and psi is equal to 1/2, you have the Doppler, you have the Lorentz-Fitzgerald equation. In other words, the theorem that I gave you is consistent with both the Doppler effect and the Lorentz-Fitzgerald equation. And so the task would be to use meaningfulness to derive that. Well, so far, we have not managed to do that. I say we because I've been working with Chris Doble on that. What I will give you is a tentative proof, which is not completely satisfactory, but gives you an idea of how it could be done. Okay, so we start with the equation LF, which is the top equation on the screen. If you use the same definition for u, you can derive the form of the O plus operation. So let's do that. So you start with the top equation, then you use your definition of u, and you derive the equation that I wrote as AV arrow. And this equation is not a known. It turns out that with psi equal 2, this equation is an equation that appears in the case of perpendicular motion. For example, in a paper published by Ungar in the American Journal of Physics in 1991. In other words, interestingly, that seemed to suggest that the Lorentz-Fitzgerald equation is related to the additional velocity by that equation rather than by the standard additional velocity. I don't know to what extent this is well known or not. To sum up, I show that both, the two pairs of equation are special cases of dE dagger and AV dagger. And as I said before, it makes sense to suppose that we should be able to derive these representations by injecting ST meaningfulness. So, this is to recall what the ST meaningfulness is. Now we have a lemma. This lemma, we have a good proof of it, so it's a solid. Suppose that one ordered pair from a meaningful LFD system is an abstract FLD pair, meaning all 5 conditions are satisfied. Then any other pair, L of alpha beta O plus beta, is also an abstract FLD pair. In other words, meaningfulness allows you to transport all 5 conditions onto all the pairs in which the scale is changing. I skip the proof. I think it's published somewhere. So we start with ST meaningfulness, and this is the equation at the bottom. And then we know that all 5 conditions are satisfied. So what that means is that we have the equation which is there. In other words, we can use the representation theorem, but the representation theorem give you a function u which may depend upon the scale, and a constant psi, which also may depend upon the scale. And so if you cancel the lambda, you get the equation, the string of equations at the bottom. Okay? So far, so good. Now suppose that the function u is the same in all cases. Number 1. Number 2, that psi is the same in all cases. Then things simplify. You get the equation which is in the middle there. The ratio nu c minus u nu v divided by nu c plus u nu v, and then the same equation but with the same ratio but with beta. Now if you work out on that equation and you rearrange, etc., you end up with the ratio beta divided by nu is equal to u of beta v divided by u of nu v. And you can show, and I will, that this implies that uv has to be equal to theta v. And the argument is pretty trivial. So what that means is that you obtain L of lambda v equal lambda, and then parentheses c minus theta v, c plus theta v to psi. But L must satisfy condition 3, namely the limit when v tends to c of L lambda v has to be 0. So this implies that theta has to be equal to 1. So the function has to be u of v has to be equal to v. The function has to be the identity. And that, of course, gives you the Doppler equation. But this result is not satisfactory for two reasons. One is the assumption that the function u and the constant psi are the same for L mu v and L alpha beta, which allow us to write that equation, is not justified. It seems reasonable, but I have no proof of it. Two, we only derive the Doppler effect, not the Lorentz-Fitzgerald equation, even though it's a special case of our representation theorem for the abstract representation. So this is work in progress. Some final comments. In the paper that I published with Guagnon in 2010, we proved the implication that the Lorentz-Fitzgerald equation implied the equivalence between R and M, which are our two conditions, and AV star. And AV star is the bottom equation here, okay? So we already knew at that time that the Lorentz-Fitzgerald equation was inconsistent with the standard representation of the addition of velocities. On the other hand, we remember that we prove that LF arrow was consistent with the representation AV arrow, which generalize the equation AV star, which arises in the case of perpendicular. I did obtain a representation theorem a while ago for the Lorentz-Fitzgerald contraction, but it was using another kind of meaningfulness constraint based on the concept of meaningful transformation, and that was published in the journal Foundation of Physics in 2004. As I said before, this type of result that I just gave you suggests that it's conceivable that we could, in time, end up with a catalog of possible functions that could be, useful for scientists. Thank you.
We have time for one question if you want.
Okay, I have a question. Yes, okay, so I can see how, for simple laws, you can clearly see how this works. But let's take something like the law that equates, in general relativity, the geometry of space-time to gravitation. Do you believe, the representation of, I think, would be extremely complex for something like this, and hard, perhaps, to get to.
But
it doesn't mean that in principle.
Look, the example that I gave you are, quite varied, right? So whether or not it could always be used, I don't know. It's debatable, and maybe the situation that you described could be split in two parts, and that may be one way to deal with it.
The quantitative structure does give, with appropriate conditions, it does give a very good intuition, I think, about the nature of the law.
Yeah.
However, I wonder how much we are manipulating too much. The degrees of freedom in manipulating conditions that have not perhaps been empirically verified. Once the conditions are there, the next step would be to empirically confirm those steps to make sure that they do, right?
Yeah.
They're consistent.
Yeah.
So
I don't know. You can't be sure, right?
that's right.
Maybe this is the whole equation, but you'll get a hint on what they are. By using someone using differential geometry, you can show that you will get at least a hint of the
right.
Well, thank you, Jean-Claude, again.